yn whole square
xn plus yn whole squared, yes,
minus
minus
xn
xn plus
minus
yn
yn
whole squared by
by
4, right? So
yes,
this, you need to show that it converts to xy, but xy I can write it as x plus y whole squared x minus y whole squared by 4,
yeah,
right? So the first term essentially says that if xn yn, so if we prove that xn converges to x implies xn squared converges to x squared, you are done with the first term, you are done with the second term.
yeah, yeah.
So
Yes, sir.
if you can prove that xn converges to x implies alpha xn converges to alpha x, which is very trivial, almost straightforward, then you
Yes,
are done with 1 by 4 also.
yeah, yes, sir.
Already you have proved that if xn converges to x, yn converges to y, then xn plus yn converges to x plus y. So therefore,
Yeah.
combining this, you'll get this. That's what I meant.
Okay, sir. No, sir.
Ah.
I was stuck in that xy, whether I should write it as x plus y whole square.
It doesn't matter, right? How does it
Okay.
matter? So you understood now, right? So this
Yes,
is,
sir.
yeah, this is what you have to prove. Hmm?
Okay, sir.
Okay, everything is in probability or almost sure. Anything doesn't matter. Okay, is that fine?
Yes,
Any
sir.
other questions? Hmm? No. Okay, so let's continue with the last class, whatever we were doing. So before that, we need to, I think, when I started the course, I said, let me just go through this if it is there here. Sorry.
Sir, you are not sharing the screen.
Yeah, I'll do that. Hey, you should have told me. I was writing. I keep forgetting this. I wrote so many things explaining your this thing. See, this is what it is. You can see the screen.
Yes, sir.
Okay. So this is, just give me a minute. The first lecture, is it lecture 0? What did I do in lecture 0? Okay, good. Something I did. Did I mention about exams and all that? When was it? Hello? Hello?
I think it is in lecture 0.
Oh, lecture 0. Did I mention or wrote? Oh, this one you are saying. Okay.
No, sir, it was in like PPT or something,
PPT?
I think.
Oh, okay. So then I should refer to, where is that PPT? Okay. Anyway, I'll get back. So do you guys remember what I said? Hmm? Saman, do you have the exams, whatever, the evaluation policy?
I'll just check it, sir, 1 second.
Yeah, because we need to have our first quiz or whatever, right? So it'll be mostly, I said collaborative mode and all that, right? So we need to have our first quiz. When do you want to have?
Yeah, should it be like derivations and derivations like that type of questions? Yeah.
No, man. So this will be mostly testing whether you have understood and whether you can apply those things properly. So it will be, I'll be testing your thinking capability, whether you can think through and get somewhere.
Okay. Okay.
Yeah. Okay. Not really a tricky question, but mostly I'll make you think and the answer. Hmm?
Okay, sir.
Yeah. Savan, if you didn't get, that's okay, but I'll write this. We will quiz 1.
Okay.
So when do you want to have, so let's look at next week. Hmm? I'll give more time for this. So basically it'll be almost 1 day. Okay. So I'll have 1 day time. So it'll be on collaboration mode. Okay. And let's have it on 14th Wednesday. No, let's have it on 13th. Okay, so it will start on 13th. 12. We have a class on Tuesday. No, right? No, we don't have a class on Tuesday.
Mathematics for data science, Tuesday, not probability class, but your class here.
Yeah. So 13th, let's start at 11 a.m. and 14th, 11 a.m. you end. Okay. This will be mostly what do you call collaborative mode. Okay. You can talk to Savan about that. The last exam was collaborative mode for them, right? So, for example, how many of you are there? 2, 2, 4, 5. Only 5? No one else is crediting, right?
Sir, this is just quiz, right? We will have also midsem, right? Or not?
Yes. I think I mentioned about midsem also, right? Yeah, we do have midsem quiz and final. I'll just get back to you on that. So I have to. I think it's there in my other computer.
Sir, what is the weightage of this quiz in the final?
Yeah, so that's what I'll get back to you. So I think I have it in the other computer. So I'll get back to you by tomorrow. Is that fine? Did I share that in the first class?
No.
So I also remember you showed some PPT. I think Praveen mentioned some PPT or something like that. And
The
you
PPT
told
has
verbally.
timings on-
Huh?
And you told verbally, I think, from PPT.
The PPT had the timings and everything in that.
Oh, I had shown that PPT. Is it recorded?
Yeah, lecture 0 we didn't record.
Oh, okay. So then I'll search for. Okay, let me just check now itself. Which lecture 0 is something? This is not the one, right? This is not the one. No, this is not the one. No, I think this is not the one. Let me just check this. If this is not the one, then I think no, I think this is not the one also. This is not a. Okay, so I think I have it in the other computer. I'll just check. Okay.
Sir, I have a question. Like, sir, you mentioned about different convergences, like almost sure convergence, probability in convergence and probability. Sir, what is different between pointwise convergence and almost surely convergence? Can you tell briefly?
Yeah. So whenever, for example, you look at the convergence, right? So you start with what is known as point. So forget about probability now. Okay. So let's assume that you are just looking at some function instead of a random variable. Okay. So when do you say that a sequence of function converges to f of x? Well, now you are looking at sequence of functions. So an example could be, 1 by nx plus 4. Okay, so this could be an example. So this I can say that as, so let's assume that x is between 0, 1, okay, for the sake of simplicity. Now, this goes from, it starts at 1 by 4 and it goes all the way to 0, right? So it's essentially it goes to 0, right, as n goes to infinity, right? This is how, if you plot this function, right, for different n, let's look at how does it look like. Okay, so n is equal to 0, how does it look like? N equal to 0, it's 1 by 4, it's a constant. Sorry, right? This is how it looks like. For n equal to, this is n equal to 0. For n equal to 1, how does it look like? It will be 1 by x plus 4. So when x is 0, it starts at 0. Sorry, it starts at 1 by 4. And then as x goes to 1, it goes to 1 by 5. So this is something like this, right? Something like this, right? This is for n equal to 1. What happens for n is equal to 2? So then again it starts here, but as x reaches 1, it will be 1 by 6. It will be somewhere like this, n equal to 2, and so on, right? So eventually what happens is it will be something like this, very, very, it will be almost like this, right? Very close to 0. So as n goes to infinity, this goes down and down, and then finally it goes to 0, except this point, right? Except this point, everywhere it will be 0, right? So now I can say the following. So as n goes to infinity, sorry, I think what happened, I'm sorry, I think I did a mistake, right? No, yeah, no, this is correct. So now what happens is, if you take any point, right? For example, if you take this point, right? So for n is equal to 0, this is the point, right? For n is equal to 1, this is what you get. For n is equal to 2, this is what you get. N is equal to some 100, this is what you get. And finally, if you look at this is a sequence of number which seem to converge to 0. That is for this particular x, let's say x0. You take any other x, right? The same observations, right? That you can observe. So that means all the points except 0, the sequence seem to converge to 0, right? That means at each of these points, the sequence fn of x seem to converge, or not seem, it converges to 0. That means it's called point-wise convergence. At every point it converges. But where does it does not converge? See, except, see, fn converges to 0 for all x not equal to 0, right? And of course x between 0 1. Point-wise, this is called point-wise, right? Now, what about x equal to 0? At x equal to 0, it has already converged to something, right? What is that number? It's 1 by 4, right? It starts at 1 by 4. This is 1 by 4, right? This height. Okay. So except at x equal to 0, everywhere it converges to 0. But now you should see this point, right? How important this point 0 is. So how do you attach importance? In this case, when you look at the usual R, the importance is in terms of length. Okay. For example, what is the length of 0?
0.
0, right? So you are saying this fn of x converges to f of x point-wise everywhere, except for a point whose length is 0, right? You agree? So in
Yes.
other words, you can say that this fn converges point-wise to 0 almost everywhere. And whenever I say almost everywhere, that means it converges to 0 at all points except for points whose length is 0. Okay. Now I will call length as a measure mu. Okay. So I'll just use a notation mu. Mu means length. So that means mu almost everywhere. That means with respect to the measure length, which is mu in this case, wherever the length is 0, it may not converge to 0, but wherever it's not, it converges to 0. Okay, you
So
understood?
then, can we say also in terms of intervals and like that, except the small interval, like here the case is
That's
only
what I'm
0.
saying. So yeah, so here it is very easy, right? Except for
Yes,
this small one point whose measure, which is length. Well, whenever you talk about length as a measure, it's called Lebesgue measure. Okay, so at that point where Lebesgue measure is 0, it doesn't converge. But I don't care about that, right? Who cares about not converging at a point which has 0 measure? I don't care about it, right? So that's when we say that fn converges to 0 almost everywhere. Which makes sense, right? Almost everywhere means everywhere, but one point which I don't care. Okay. Is this fine?
yes.
Okay. Now,
This is point-wise convergence. Yes, yes.
well, strictly speaking, it's almost everywhere. The subtle difference here is that it doesn't converge point-wise at a point or on a set whose measure is 0.
Then sir, point-wise means like in every point, like for the domain of the function, for every point it will converge. I mean,
So
yes.
if I say that Fn converges to F, that means Fn of x converges to f of x for all point x in the domain of F. When this happens, then we say that it converges pointwise. Okay, so this essentially means that when I say limit n tending to infinity fn of x, because if I fix x, fn of x is a sequence of numbers. You know what is the limit, right? So limit is epsilon delta definition of limit, right? That will be equal to f of x. F of x is also a number the moment I fix x, right? So if this happens for all x in the domain, then we say that fn of x converges to f of x pointwise. Now, what is happening here in this example? Well, it's converging to 0 for all points in the domain except for one point. But do I really care about that point? Not really, because it has measure 0. Then we say that it converges almost everywhere to 0. Okay, so here also I can say fn converges to f mu almost everywhere. What does that mean? It means that fn of x converges to f of x for all x, okay, in some set A, which is of course a subset of the function, with the measure of, oh well, I'll put it like this. So it converges to this with measure of, you take, for example, the domain of F, remove A, okay, the measure of this is 0. That means wherever it does not converge, the size of that set is 0. Then we say that Fn converges to F almost everywhere. Is that fine? Well, these are all notations, but roughly what I'm saying is it converges to pointwise to F at all points of interest. What are the points of what are the points which are of not interest to us? Those are the points with measure 0. I don't care about that, right? Is that fine?
Yes, sir. Yes, sir.
Yeah.
Sir,
Yes.
sir, in case of this fn going to f, no, sir. So, like in your first example, we can take fx as 1 by 4 when x is equal to 0 and 0 when x is not equal to 0. So this fn is going to this function f. So why we are excluding this option like 1 by 4? Like we are just
Yeah, you can always say that. I'm not saying you should not. Okay, so
Yes,
let me
yes.
put it this way. Okay, this example, right? I can say Fn converges to 0 almost everywhere. In fact, mu almost everywhere. But
Yeah,
Fn
this
converges to some function f, which I'm going to define pointwise, where f is 0 for all x 0, 1, 1 by 4 for x equal to 0. As
0.
you're happy now, Sumit?
Yes. So actually we are just looking for the function of interest, no sir? Like here I am not
the
interested in
function of
1 by
interest.
4.
I'm looking at function where it behaves, or I'm looking at the behavior of the function over sets of interest.
Okay,
right?
sir.
If you look at it in terms of probability, if you are looking at the behavior of a sequence of random variables, for those outcomes of 0 probability, what is the point, right? I mean, it never occurs. Why are you bothered about the convergence?
Okay, sir.
Right?
Okay, sir.
So whenever you look at convergence of random variables, you better look at those outcomes for which the measure is not 0. I mean, it occurs, and therefore you should be worried about the convergence, right?
Okay, sir.
Do you agree?
Yes, sir. Yes, sir.
Is this fine? I know. I mean, it's when I looked at this for the first time, it's highly non-trivial. Okay, I took some time to digest. For example, almost sure all these convergences. Okay, so it's not, if you are a little concerned, don't worry. Okay, it's good that you are concerned, and then you will start thinking more about it and figure out. Okay, I'll try to help you as much as I can. Yes, Rishabh.
So also in the definition of almost sure convergence, there you mentioned a thing like a set of probability 1 with probability 1.
Correct.
So is it like somewhat connected here, measure 0 or like probability 0 and their probability 1?
So now, whatever mu that I talked about, right? If you are looking at probabilities, that mu will be probability. Okay. All that I'm saying is, see, if you look at this definition, right? Where is that? This definition, right? What I'm saying is, look at all those points where Fn does not converge to F has measure 0. If it is probability, it says, okay, suppose, okay, what do you mean by, okay, so what do you mean by Xn converging to X almost surely? Okay, the moment I say almost surely, that means the measure is probability measure. Okay, so now what do you mean by this? This essentially means that Xn of omega converges to X of omega. Just look at the parallel, okay, between these two. For every omega in omega, okay, omega is your domain, right? So Xn is a mapping from omega to R. So omega is your domain of Xn or X for that matter. For every omega, such with the probability of, sorry, I think, okay, I'm sorry. So omega belonging to a set A, which is a subset of omega, right? Omega is your domain of F, A is your set of interest, with probability of, you look at omega, right? Remove A, the probability of that should be 0, right? Okay, what is this set? Let's expand this. Okay, so what do you think is this set? It is all those outcomes which belongs to omega but not yet, right? So this is probability of all omega belonging to omega, remove A. So what does that mean? This means probability of all those omegas such that omega belongs to omega, removed A. What does that mean?
Sir, Xn omega does not converge to X
Yeah,
omega.
Xn omega does not converge to X of omega, which is 0. That's what I'm saying. Now, if this is 0, what if probability of something is 0? What is probability of complement?
1.
Can somebody tell me? Guys, you should be quick and answer.
1,
Okay.
sir.
1, right? So
Yes, sir.
what is the complement of this?
So omega says that Xn of omega are going to X omega.
Converges to X of omega, which is 1.
Yes, sir.
Rishabh,
This
is that
is
fine?
almost sure.
Yeah, this is almost sure. Okay, so Sumit is attending measure theory course. So there, Amlan never talks about this thing. Okay, he only talks about this almost everywhere, because the measure that he is considering is a very general measure. It could be a probability measure, it could be a
Yes,
Lebesgue
sir.
measure, or it could be something else, right?
Yes.
Whereas we are very focused and we are talking about only probability measure. The language is almost sure. Okay, is that
Okay,
fine?
sir.
It
Yes,
makes
sir.
sense also. Almost everywhere also makes sense, and almost surely also makes sense. Surely means with high probability, right? Almost everywhere means everywhere except for some sets which I don't care. Okay, both are required. Is that fine?
Yes, sir.
So that means that for almost surely we are only interested for our set of interest A.
Correct. Yeah. So a set A whose probability is 1, if Xn converges to X on that set A, then I'm happy. I mean, I say that Xn converges to X almost surely, because whenever Xn of omega does not converge to X of omega, those outcomes has 0 probability. I mean, it will never occur. Why bother? Right?
Yes, sir. Yes.
Right, see, it's like this. I don't know, you are investing, okay, so and you are looking at returns. X1 is the return today, X2 is the return tomorrow, and so on. And I somehow see that this sequence converges to some $1,000 every day. Okay, so it converges to 1,000. What does that mean? Every day I'm going to get 1,000 rupees profit. Okay, but this is for all omega. There is outcomes where things are under control. Suppose, you know, some disaster happens and you will lose money heavily, then the question is, should you invest so that the return is 1,000 rupees every day? Well, you should, right? Because the probability of that disaster happening is almost zero. That means almost everywhere or almost surely XN converges to 1,000. So I better invest and make money, right?
Yes, sir.
Right?
Mhm.
That's what it says. Is that fine?
Yes, sir.
Others? Rishabh?
Yes, sir. Yes, sir.
Yes. Ayush?
Yes, sir.
Jayant? Of course, Praveen? Yeah.
Yes, sir.
Okay. Jayant? I think you should unmute Jayant. It doesn't seem to. Okay, anyway. Okay, so this is about convergence, but let's go back to I think whatever we were discussing in the last class, right? So we were looking at this result, right? X. Sometimes I write this, okay? What do you mean by this? If I say x greater than or equal to 0, almost surely, what does that mean? Anybody? Okay, you can make a
Means, sir,
guess.
the point at which x is not greater than equal to 0 has the probability measure 0.
Can somebody refine that? Of course, it is correct, but in terms of probability language, can someone else refine? Ayush, can you refine this?
Sir, maybe positive random variables.
That's correct, but it essentially means that the outcomes for which xn of omega is less than 0 has 0 probability. Okay, that's what
Yeah,
it
yeah,
means.
yes.
Yeah, that's me. Okay, so that means it's a non-negative random variable. Okay, expected value of x is what? Limit n tending to infinity, expected value of x n, right? This is what we had, right? Is that fine? So let's look at a proof of this, but there are several different ways of proving this, but I try to sort of simplify this, and let's see if that proof works. Okay, so for example, okay, so before this, then I'll just make some notes. First of all, we say that f of x is order of g of x. You know what this means?
Yes, sir.
It essentially means that if you take limit extending
Yes,
to infinity, f of x over g of x, it's a constant. Okay, I can say, for example, how do I log x over x? Okay, it's order of 1 by x. Why is that? Is that correct? It's not correct, right?
The capital was.
Yeah, so capital O, that's what I'm talking about. So it essentially says the rate of growth. Okay, so if you look at the ratio and x going to infinity, it's a constant. So it's the rate of growth that I'm talking about. Okay, so instead of saying 3 plus, let's say, root x by x, right? So this is order of 1 by root x, right? Because 3 over x goes as 1 by x. Root x over x goes as 1 by root x, which is lower than 1 by x. So it's of the order of 1 by root x, right? So it simplifies the notation a lot. Okay, so with this, let's move further. So what is the expected value of x, minimum of x and this? So I can write this as 0 to infinity, x minimum n. Well, I can write this as fx of x dx. Okay, I'll write it like that only. So what is this? This is from 0 to n. If it is from 0 to n, minimum of x and n is x, right? X fx of x dx plus from n to infinity. So minimum of x and n would be n, right? N fx of x dx. So this 0 to n x fx of x dx plus n times probability that x greater than n. This is what we have, right? Now, what happens as n goes to infinity, right? So suppose, right, expected value of x itself is infinity, right? Then it doesn't matter. Why? Because as n goes to infinity, I don't care what happens to this, as long as it converges to some, as long as it doesn't matter, because this first term, as n goes to infinity, it goes to expected value of x, which is anyway infinity, right? The first one goes to infinity. Nothing to prove, right? Right? On the other hand, because it goes to infinity, nothing to prove. On the other hand, if so, we'll assume that assume expected value of x to be less than infinity. Okay. Now let's see what happens if expected value of x is less than infinity. As n goes to infinity, the left hand side is equal to expected value of x, provided this goes to 0, right? Then need to show that n times probability of x greater than n goes to 0 as n goes to infinity, right? Otherwise, if it doesn't go to 0, suppose it goes to a constant, right? Then what happens? This will be expected value of x, and this will be a constant. So it will be expected value of x plus constant. That's not what we were supposed to show, right? So we should show that both are, the left hand side is equal to expected value of x. So we want this to happen, right? So now how do you show this? Well, let's see. So when will this happen? This is how if you give it to a mathematician, he wouldn't probably do it this way. He will do exactly opposite. I mean, he will not ask reverse question. This is the thought process, right? So
we can you just mentioned the order, so we can if we can calculate that n into probability of x greater than n, the order is of the form 1 upon n, then we can done with it tends to 0.
Order 1 over n goes to a constant, right? It doesn't go to 0.
So 1 upon
n
n squared.
N squared is too much to ask for, right? So there's no guarantee that it will be n squared.
Sir,
Right?
I told about the product. The order of the product is of the form 1 upon n.
Well, that's also too much to ask for, right? That essentially means that probability of x greater than n is of the order of 1 by n squared. But
Yes.
what is the guarantee that this is n squared? Okay. So now let's look at this. Expected value of x, I can write this as 0 to infinity, probability of x greater than t. Do you agree? So I'm saying this is less than infinity. So what does this mean? This means that if I integrate from some n to infinity, probability of x greater than t, this dt, this goes to 0 as n goes to infinity, right? Do you agree? Because if I'm integrating the function from 0 to infinity and that happens to be finite, then if you take a partial integral, that is from n to infinity, and take n to infinity, then the integral should go down to 0. Otherwise, you will never get finite, right? You will always get infinity as answer. Do you agree?
Yes, sir.
Everyone?
Yes, sir.
Yes, sir.
Okay, Jayant? He seems to be not there. Okay.
Sir, it
Now-
is like a tail of the convergence series, no, sir?
Yes, right? So it's almost like
Yeah.
summation xn, right? N equal
Yes,
to
sir.
capital N to infinity. So if the overall n equal to 1 to infinity is finite, n equal to n to infinity is the partial sum, that should go to 0, right? Otherwise, no, the sum won't converge to finite value, right? So when will this happen? This will happen provided probability of this is of the order of 1 by n power, right? So for sufficiently large n, it should be of the order of, sorry, not n power, right? So what should be the answer? It should be t power, right? 1 minus alpha, right? Sorry, is that correct? No, sorry. This should be, it cannot be 1 by t, right? It should be, if it is 1 by t, it goes to infinity. Do you agree? It will
Yes,
be
sir.
ln t,
Log.
so it goes to infinity. So it should be slightly better than 1 by t, right? Epsilon should be greater than 0, right? Do you agree? At least this, right? So provided this is,
So why not 1 by t itself? You're taking the tail integral, right?
but what happens if you take 1 by t? It's
This is not
ln
starting
t.
from 0, right?
Huh?
It's not starting from 0, so 1 by t also should work, right?
Just compute and tell me what will be 1 by t.
1 by t integral, okay.
Ln
It's ln t,
ln
right?
infinity.
Ln infinity is infinity, right? So that's the
Yeah,
problem. Okay, but if you look at 1 by t plus epsilon, right? So what will be the answer? It will be, so I can write this as t power minus 1 minus epsilon plus 1, which is t power minus epsilon, right? So 1 by t power epsilon as in n to infinity, right? So infinity is 0, n is what? 1 by n power epsilon, right? As n goes to infinity, that goes to 0. So at least it should be this much, right? Is this fine?
Yes, sir.
So now if I substitute, therefore, this implies n times probability of x greater than n should be at least n times order of 1 by n power 1 plus epsilon, which is nothing but order of 1 over n power epsilon. So this goes to 0 as n goes to infinity. Okay. So this is something that I came up with. I think there are no flaws here, but if you find some flaws and correct it, I'll give you 5 extra points towards the final average marks that you get. Okay. Is this fine?
Hello, sir.
Yes.
Sir, can't we use Markov inequality here?
How do you use Markov inequality? What do you mean by that?
N into P.
It's a very bad idea, right? So use Markov inequality. So you're saying this one?
Yes, sir.
So if you use this, it'll be n times expected value of x by n, right? You get expected value of x. It's a very bad bound, right? If expected value of x is 4, you are saying this is 4, upper bounded by 4. Of course it is upper bounded by 4, but what I want to show is this should go down to 0 as n goes to infinity. That's what I want to show. Right? I don't know if everybody knows this particular thing. I think it was a part of homework, right? This thing for positive random variables. Yes or no? I think we saw this for discrete random variables, right? Expected value of x for non-negative random variables, discrete. It's summation probability of x greater than some k equal to 1 to infinity, right? Something like that. Yes or no?
Sir, in that there was condition like with probability 1, like there was condition also, no? That the probability should be 1.
Probability of what?
Sir, wait, I will tell you. So it was something like, suppose x is greater than 0 with probability 1.
That's what it is, right?
Okay, I almost sure. Okay. Okay.
Okay. Yeah. Fine. Everyone okay with this?
Yes, sir.
Okay. So this sort of completes something that we took in the last class. Let's move on from here. Okay. So there's something known as monotone convergence theorem. Okay. So this is also super important monotone convergence theorem. Okay. So what it says is you take of course, non-negative random variable x1 less than or equal to x2 less than or equal to and so on. Okay. And let's also assume that this limit exists, that is, and xn converges to x almost surely. That means probability of xn converging to x is 1. Okay. Right. Then expected value of xn limit is expected value of x. Rishabh, are you, I mean, one of the questions that you asked in one of the classes was whether you can interchange the limit and integral, right? So expectation is basically integral, and there is limit outside, and I'm pulling it inside, and I'm saying both are equal. In fact, the limit here is in the almost, I mean, when I take the limit inside, limit xn is equal to limit of limit xn is equal to x almost surely, probability 1. Okay, so now yeah, so that sort of partially answers your question, because this doesn't say that if you take any sequence you can interchange. It only says that it should be a monotone sequence, right? x1 less than or equal to x2 less than or equal and so on. Then only this is true, right? So now the question is, how do you prove this, right? So what do you think is the idea of the proof? Any idea on how to prove this? Yes. There is one subtlety, right? So you know, if you look at this, right? So okay, let's look at the proof. So expected value of xn, right? I can, instead of looking at this, what we will do is we will do the following. So you fix some large xn, okay? Fix some, well, this is slightly sloppy, large n. What do you mean by large? Let's see later. Okay, some large n. Consider this. Let's say yn, which is xn n. You know what this is, right? And y, which is defined as x minimum of xn n. Okay, is that fine? Now suppose I prove that you know, yn converges to y. Okay, so let me call this as yn comma capital N. Okay, this is capital N. Okay, so for every n, right? Okay, sorry. Suppose expected value of this is equal to, goes to this. Okay, it is true for every n, right? So this implies limit n tending to infinity, expected value of yn is equal to limit n tending to infinity, expected value of yn, right? So what is this? I mean, this whole thing, limit of n tending to infinity, expected value of yn comma n. Yn comma n is what? Xn, minimum of xn and n, right? By previous theorem, this is nothing but expected value of what? Xn, right? Limit, right? Limit n tending to infinity. That is something that we already have, right? Did I write this correctly? So this goes to infinity for every n, right? So this is what we have, right? So expected value of yn is this. As I take limit n tending to infinity, I get this, right? This is equal to expected value of x. That's what we get. Okay, so now that essentially means that I have to show this. I'm done, right? Show this. Is this clear?
Sir, in the statement of monotone convergence theorem, sir, can you just tell me, sir, what is the like monotonic sequence of random variable?
Monotone means this. This is monotone.
So that I understand, but sir, I cannot imagine like how a a sequence is monotone, like
So okay, so I can do this. So let's say okay, so I'll write it in different colors. So example, x1 of omega, or in general xn of omega, is let's say 1 plus e to the power minus n by omega. Omega is between, let's say, 0 to sorry, I don't want 0 here, maybe a plus omega, so 0 to 2 pi. Okay, so this is an example, right? So as n goes to infinity, what is happening here? Well, I think how do I put it? It's going down. Okay, fine. So this is also fine. I'll take a negative sign here. Okay, so I can say that x1 is less than or equal to x2 is less than or equal to, and so on, right? And xn converges to what? As n goes to infinity, it's minus 1 by omega plus a, right? Is that fine?
sir, okay.
See,
Okay.
I can rotate a wheel and that will give me the outcome omega, right? Some angle between 0 to 2 pi. Xn of omega is some function. Maybe I'm computing something as a fraction of that angle, which is given by minus 1 plus e to the power minus n over a plus omega. So this represents something I written or whatever, right? So this is an example. Okay, is this okay?
Okay, sir. Okay.
Now let's look at this guy. Okay, so let's see what is the difference of. So let's look at ynn minus yn. Okay, let's look at this difference and show that this difference when you take expected value goes down to 0, right? As small n goes to infinity, right? Since expectation is linear, that proves this particular thing, right? So this thing. Okay. So now,
Sir,
yes.
sir, limit is over a small n. No, sir, you have written on a capital N.
Both, right? So eventually I have to take over capital N, because expected value of x, minimum of xn and n, as n goes to
Yes.
infinity, is expected value of xn, right? So that's the idea.
Okay, sir.
See, I know that xn is smaller than xn plus 1. Okay, keep that in mind. Okay, we may need this. Okay, so I'll probably write the other way. I want it to be positive. So yn minus ynn. Okay, so let's look at the expected value of this guy. Okay, so what I'm going to do is I'm going to split this into two events. Okay, one is a bad event and the other one is a good event. So I can write this as expected value of this difference, yn minus ynn. Indicator, I'll denote the bad event. That is, if you look at x minus xn, right, this difference is small. Okay, plus I'll take another event, ynn. Let's see if this works. I think it should work. Greater than or equal to epsilon. Do you agree?
Yes, sir.
Okay, so if x minus xn is less than epsilon, what can you say about the difference?
Sorry, sir. Can you repeat, sir?
If x minus xn is smaller than epsilon, what can you say about yn minus yn comma n? Okay, let's see. Let's look at what is yn minus yn comma n. So this is x minimum of this minus xn minimum of this. So xn
It will be 0.
You agree? If you agree with this, do you agree? See, you are earning some money and I am earning some money. Okay, and government has put a cap. Let's say if you earn more than $1 million, then you have to give away the remaining whatever you earn above 1 million. Okay, both of us. Okay, suppose that is the case. If I say that whatever the money that I have earned, okay, that is X and Xn, let's say, the difference is less than 10 rupees. Okay, then even after government putting a cap, whatever money that I have, if I look at the difference, that should also be less than 10 rupees, right? Do you agree?
Yes, sir.
Is this okay, everyone?
Yeah, sir.
No, everyone, not Sumit.
Yes, sir.
Huh?
Yes,
Okay,
sir.
Rishabh?
Yes, sir.
Yes? Okay, fine. So this is less than epsilon. So what I can do is whenever this event happens, this is upper bounded by epsilon. So what I will do is I'll upper bound this by epsilon times expected value of indicator of x minus xn less than epsilon, right? This is what we have. Plus, what about the other term? See, let's look at this, right? Whenever x minus xn is greater than epsilon, what can you say about this difference again? See, minimum of x and n cannot be more than n, right? Capital N. Minimum of xn and n cannot be more than n. So the difference cannot be more than n, right? So I can say it's upper bounded by n times expected value of indicator of x minus n greater than or equal to epsilon. Okay.
Yes, sir.
Fine. So this is nothing but you are almost done, right? So you have epsilon, right? So this is probability that x minus xn less than epsilon plus n times probability that x minus xn greater than or equal to epsilon. Now what happens? See, this actually this goes to, as n goes to infinity, x minus xn goes to 0. So probability that xn minus x minus xn less than epsilon is 1, right? Because it's almost sure convergence. So this goes to epsilon, right? So this is true for every epsilon, right? So I'll just modify this. For any epsilon greater than 0, we have all these, right? So that means this goes to epsilon. So since this is true, since epsilon is arbitrary, we are done. Okay, are we done? Whatever, I'll leave it done. So are we done?
Yes, sir. If it is a less than epsilon for the arbitrary epsilon, then it is
So what have we shown?
true,
We
sir.
showed that yn minus yn comma n goes to goes to 0, right? Since epsilon is arbitrary and then goes to infinity, right? But what can you say about this yn minus yn comma n? This thing, this is always greater than or equal to 0, right? Almost surely. Because x minus xn is always non-negative, because x is always larger than xn. Because xn is smaller than xn plus 1, which is smaller than xn plus 2, and so on. Eventually it reaches x, so x is always larger. So this sort of says that we are done, actually, right? Is this fine? It's nice, right? Monotone convergence theorem. Now you know, Rishabh, you know when to exchange limit and integration, right?
Yeah, so we have to see the monotonic monotonic.
You know, I mean, you should be very lucky to encounter a monotone sequence, right? In reality, the sequence could be something else, right? It will not be monotone. It can be oscillating and going up, or oscillating and going down and reaching something. So it's not really a monotone sequence.
Sir, about monotone, sir, it can be monotonically increasing. Also, it can be monotonically decreasing, or one way, only one way around.
No. It's the other way is very easy, right? If it is monotonically decreasing, I'll take minus of that, which is monotonically increasing. I'll apply monotone convergence theorem for that and remove the minus sign later. That's all. Right?
Okay. Yes,
it's a straightforward thing. Now, is it useful? Right? Always. Not really, right? So in many of the cases, this is not at all useful, right?
Hello, sir.
Yes.
Sir, what if E of x is infinity?
Huh?
What if expectation of x is infinity?
I'm saying this goes to infinity. That's all.
So limit
How
intending
does
to
it go?
infinity.
This is also infinity. This is also infinity.
Okay.
Yeah, that's all. There, it's yeah. You go ahead and interchange the limit. Anyway, you're going to get infinity. So who cares, right? Right? It won't be interesting, but yeah, it is true. If you look at it from a pure mathematics point of view, if it is infinity interchanging the limit, you can still interchange the limit and integration. It won't be like, for example, you pull the integration. So it's like this, right? So I can give you a very good example. What is the answer? And let's do this also. What is the answer for this? Hey, please tell me what is the answer for this, man?
0.
0, right? Because the limit is 0, so integral of 0 is. What is the answer for this?
Also
Infinity,
0.
sir.
Ln of nx from 1 to infinity. So obviously you'll get infinity. So this is not equal. So you cannot interchange limit and integration, right? Do you know why this is the case here? Okay, this gives us some more insights, right? So what is happening here?
Sir, here the sequence is like 1 by x, 1 by 2x, 1 by 3x, 1 by 4x, like that, right?
Correct.
So we cannot, can you not tell it is monotonically something or not? Because for a fixed value of x, it's
Yes.
like decreasing.
Yeah. So now what is the issue? So I think it comes back to this guy's question, right? Our Raveen's question. What is happening here? Huh? Hmm?
Sir, maybe it works only for a finite expectation.
Correct, right? So if it's possible that your expectation, right? Uh, okay, so let's think. So not here it is the case, but if it is probability, it is something different, slightly different. But what is happening here, right? So it's a monotone sequence, right? It's bounded also because n equal to 1, I get 1 by x, right? So anyway, it's bounded by 1. It cannot be more than 1. It cannot be less than 0 because it's a non-negative variable, right? So now, why can't we interchange the limit and integration? Why? Sumit, any thoughts?
Sir, integral has to be finite, I think, sir.
Which integral has to be
Like
finite?
integration 1 to infinity 1 upon nx, whatever we are calculating over here, it has to be finite, sir. For each if
Yes, right.
if I is fn, sir.
So if expected value of xn itself is infinity for some n, right? See, for example, in your case, let's go back here. Suppose for some n, expected value of xn is infinity. Let's say x for certain n, let's say n small n, expected value of xn is infinity. Then expected value of xn plus 1 is also infinity. Expected value of xn plus 2 is also infinity, and so on. You get a sequence of infinity, and the left hand side is infinity, right? But expected value of x need not be infinity, right? So now the question is, let's go back to Praveen's question. What if this is infinity? Expected value of x is less than infinity, or let's say this itself is infinity. Can you give an example of that kind here? Each one is not, but overall it is. Can you give me an example? So n e power minus x, right? See, each one will give me what? N e power 0 to infinity. Okay, so 0 to infinity e power minus x dx is what? 1. So you get n, right? On the other hand, for each, so n equal to 1, you get 1, 2, 3, and that kind of a sequence, right? If you pull this to inside, as n goes to infinity, n times e power minus x is infinity. So integral of that is infinity. You already have infinity. But the moment you take limit, these two becomes equal. Okay. So at least from an example, we can see that, right? So if we want this to be, this can be arbitrary, but we want this to be finite. Expected value of xn should be finite. Is that okay? It should be finite for all n. That's the thing.
So actually, sir, in major theory, sir,
Hmm.
we have to check the function f. So we first construct a simple functions sequence of simple functions converging to that f, no, sir.
Correct.
And these all fn's has to be integrable, as it is a simple, so it is a integrable, and everything has a finite value. So in a similar fashion, if we think over here, then for each xn, then expected integral should be finite, sir. Like expectation of xn has to be finite for each n.
Exactly. Yeah.
Then
But the limit need not be.
yeah, limit, we are not talking about the limit, but the expectation of xn, each xn expectation has to be finite, sir.
So for those who don't know what a simple random variable is, it's you can think of it as a discrete random variable. So how do you can approximate a continuous random variable by discrete random variable, right? So that's what he's talking about. Okay. Any questions? So now the next thing is, how do we generalize? Okay, so we will ask this question, and in the next class we will answer that and move on to how do we generalize. So in the next class we will look at a very important theorem called two important results called Fachow's lemma, and the other one is dominated convergence theorem. Okay. So that will sort of tell you when can you really exchange limits and expectations. Okay. So whenever you encounter expected value of xn and you want to take a limit, then you will know under what condition you can interchange. That is given by dominated convergence theorem. Okay. Is that okay?
Okay. Yes, sir.
Right. This is something very important. Later on, we will sort of use it. Some of these. Once we do this, we will. So this part, right? I'll maybe LaTeX this part and send it to you. Okay. I'll take some time, but especially the until the monotone convergence theorem from whatever results that from yesterday till to next class. Okay, that part I will LaTeX and send it to you. The remaining anyway, I'll follow Gallagher's book. Okay, yeah. Any questions? Any questions? No questions.
Sir, no, sir. Sir, actually, sir, I was thinking the quiz is on 14. So before that, maybe we will go through all the resources, what we have done, and maybe jot down and ask you if any doubt we have.
Yeah,
in the next.
So maybe we will schedule a small discussion session. Okay, either in the class itself or an extra. Maybe I think we missed one class, right?
Yes, sir. I think. Yeah.
So we will compensate that by some kind of a tutorial / discussion session. Okay.
Okay. Okay.
Yeah. Good. Okay. Yeah. If there are no questions, then I'll stop. Ayush, you have any questions? Raveen?
No, sir.
No.
Hello, sir.
Raveen? Yeah. You have any question?
Sir, in central limit theorem,
Mm-hmm.
so we are taking Zn equals sum of random variable by root n.
Mm-hmm.
So you are telling that Zn converges to Gaussian PDF.
Correct.
So I mean, what does that actually mean, sir? I mean, x1, x2, xn are sample values are
these are random
individually
variables,
PDFs.
right? No. So you should not get confused with that. So Did you do that experiment? I had asked you to write a MATLAB or whatever code to simulate central
sir.
limit theorem, right? Did you get a
Yeah.
chance? Did you do that?
Yes, sir.
Huh?
Sir.
So what did you do there?
So I took some 1,000 random variables x to x1 to x,000 exponentially distributed,
Okay.
and I
Perfectly
took
fine.
sample size of some 10,000, something like that.
Okay, fine.
Then I added them column wise, like you get a matrix, right?
It's not a matrix, right? It's exponential.
No, sir. Each x1 contains 1,000 samples.
Okay, fine. Yeah, true. Okay, so each one of them is like exponential. That's what you're saying.
Yeah.
Okay, fine. Okay. Yes. What did you do after that?
Then I summed them, then divide by root n. Then I got some vector.
Correct. Let me call this as x, some capital N. Okay. Then?
Oh, sir, I'm asking, is it right or like?
Okay. What did you do after that?
I plotted the histogram, sir. It
Perfect,
was
yeah.
like Gaussian.
So it will be something like this, right? This will be mean will be 1.
Root 10 times mean of x.
Yeah, root n. Mean of x is 1, right? I'm assuming exponential with mean 1. Right? And the variance corresponds to the variance of x1, right? Whatever that is. Is that what you got?
Yes, sir.
Okay.
So we should vary number of sample, like here we are having two variables, right? N and sample sizes.
Correct.
So we should vary n and sample sizes. Both are only fixed sample size and vary n.
See, these samples, right? These samples that you're taking, right?
Yeah.
That is a different marker. These samples, these are realizations of xn's. Right?
Okay. Yes.
Okay. Across this is like x1 is one random. So think of each column as n outcomes of an experiment. Okay.
Okay. Sir.
Yeah. Something happened. Is that fine? I think I lost it. Oh my god, there's some issue. That's why I hate Windows. Something or the other, it keeps coming. Okay, I lost only this much. Okay. Any other question? Any other questions? If not, we'll stop here or what?
Okay, sir. We'll ask in the next class maybe. Yeah.
Yeah, sure. Okay. Thanks.
Okay.
Savan, can you please stay back? I think others